Welcome to The Explainer. Today, we're unlocking the secret power of moss, from bog bodies to climate control. It's an organism you probably walk right past every single day without a second thought. But beneath that humble green appearance, well, it's actually a masterful, almost magical preserver that has literally shaped human history and our global environment for millions of years. Okay, let's dive right into this. What on earth could possibly connect surgical bandages used in the muddy trenches of World War I, ancient Iron Age human remains found in Northern Europe, and the massive modern fight to maintain the balance of our global climate? Right? It sounds like the setup to a bizarre historical mystery. But the answer to all three is moss, specifically a type of peat moss known as sphagnum. Throughout this explainer, we're going to unpack exactly how this single ancient plant lineage manages to be the absolute key player in all of these vastly different arenas. So to really understand its power, we've got to start down at the microscopic level, looking at bryophytes versus vascular plants. The vascular plants you're used to seeing, think trees, ferns, the flowers in your garden, they feature complex internal tissues, like deep roots and a whole internal plumbing system. Mosses, on the other hand, belong to a simpler group called bryophytes, which completely lack roots, xylem, and phloem. They don't have true roots at all. Instead, they just use these simple root-like threads called rhizoids, basically just to anchor themselves down. And their leaves? Often just a single layer of cells thick. But hey, don't let that structural simplicity fool you. By lacking all those complex tissues, moss is highly efficient, absorbing water and nutrients right through its surface, straight from the air and rain. Now, what's really interesting about this is this absolutely staggering number, -100 megapascals. This represents the extreme water pressure of desiccation or dehydration that a moss cell can actually endure. To put that into perspective for you, a typical vascular plant, like a tomato plant or a rose bush, is going to hit its permanent wilting point and die at around -1.5 megapascals. Mosses? They can survive a dry environment nearly 100 times more severe than that. Almost all of their external water can be lost without actually destroying the cell. It's literally a biological superpower. And this extreme survival skill all comes down to moss being what biologists call poikilohydric. This defines an organism that lacks control over its water retention, allowing it to rapidly lose and gain water to survive extreme dehydration. Because moss lacks that complex internal plumbing we talked about to control water, it's completely at the mercy of its environment. It rapidly loses water when it's dry and soaks it right back up when it's wet. When a severe drought hits, the moss basically enters a state of suspended animation. The cells undergo this wild process of vitrification, essentially turning into a biological glass to protect their internal structures. It looks totally dead and dried out. But the very second moisture returns, boom, protective and repair mechanisms instantly kick in. The moss resurrects from a completely dehydrated, shriveled state right back to a living, green, photosynthesizing plant. No way, right? When you've got a plant with these kinds of intense physical properties, humans are definitely going to take notice. Zooming out to human history, there are some truly unbelievable uses of sphagnum. Different cultures have capitalized on it for thousands of years. Thanks to specialized porous dead cells in its leaves, called hyaline cells, sphagnum can absorb up to 20 times its own dry weight in water. Because of that incredible absorbency, Michigan Chippewa Indians ingeniously used it as baby diapers, keeping their infants clean and warm. Over in Northern Europe, Scandinavians traditionally used moss for house insulation and even lined their boots with it against the bitter cold. And incredibly, archaeologists have unearthed 1,800-year-old wooden kegs packed with butter and cheese that were buried in sphagnum bogs purely for preservation. That wild absorbency actually brings us right back to our initial mystery. The British Army used approximately 1 million pounds of sphagnum dressings a month. During World War I, cotton became incredibly scarce and super expensive. But obviously, soldiers still desperately needed sterile, highly absorbent surgical dressings for their wounds. The solution? Sphagnum moss. By the end of the war, the British Army alone was hitting that million-pound mark every single month. Not only did the moss absorb blood and fluids way better than cotton, but it also naturally inhibited bacterial growth, which saved countless lives from secondary infections in the trenches. An absolute game changer. So you're probably wondering, how exactly does moss prevent those infections and keep 1,800-year-old butter perfectly fresh? Well, meet the secret preservative, sphagnum. It's a pectin-like polymer found right in the cell walls of the peat moss, and it literally halts microscopic decay. Sphagnum actively lowers the pH of its surrounding environment, making the water highly acidic. Plus, it locks away the vital nutrients that bacteria actually need to survive. The end result is this cold, highly acidic, and anoxic, meaning oxygen-free, environment. Microscopic decay is just stopped dead in its tracks. The moss is actively engineering its environment to become a perfect, natural time capsule. Let's move to and see how this builds into an almost unimaginable scale of preservation. Thanks to sphagnum and those anoxic bog conditions, researchers have uncovered things that completely defy time. Just look at this timeline. We have the famous Toland Man, deposited in a Danish bog way back around 840 BC. Then there's Grubble Man from the 2nd century BC. And it's not just human remains either. Science recently revived a sample of Antarctic moss that had been frozen under the ice for 1,533 years. And guess what? It went right back to growing. The preservation capabilities of this organism literally span centuries and millennia. Let's take a closer look at those Iron Age secrets in the peat, because these bog bodies are a total archaeological treasure trove. When these humans were pulled from the peat, they weren't just skeletons. Their skin, hair, and internal organs were flawlessly preserved. This has actually allowed us to see intact wounds and evidence of blood rights. Growball Man, for example, had his throat deeply cut, while Tullen Man was found with a rope around his neck. Now, some historians interpret these as ritualistic human sacrifices, while others view them as criminal executions. But the moss? It's completely impartial to morality. It just preserves the facts of their end. We can even analyze their stomachs to find their very last meals, like the edible weed Chenopodium, and even identify whipworm parasites perfectly preserved right there in their intestines. And this brilliantly illustrates how the moss's power of preservation scales way up to impact the entire planet. Sphagnum moss doesn't just preserve butter and Iron Age bodies, it preserves cardin. When sphagnum dies, the acidic conditions it created prevent it from fully decaying. So over thousands of years, this partially decayed moss builds up into deep, deep layers of peat. Globally, peatlands contain an estimated 400 gigatons of organic carbon. That is a massive 30% of the Earth's entire soil carbon budget. By locking all of this carbon underground instead of letting it rot and release CO2 into the atmosphere, moss acts as this massive global climate controller. But this immense carbon vault brings us face to face with a really complex modern controversy, balancing sustainable resource extraction versus risking global carbon release. See, peat is highly valuable. We harvest it as fuel for heating, as an incredibly effective soil conditioner for agriculture, and for various industrial uses. However, to harvest it, you have to drain the bogs. And when we do that, we introduce oxygen back into the system. Suddenly, the moss begins to rapidly decay, and we run the very real risk of releasing those 400 gigatons of sequestered carbon straight back into the atmosphere. The tension here is huge. We have to weigh the human and economic need for resource extraction against the severe environmental risk of accelerating global carbon release. Now, everything we've been discussing today isn't just a bunch of fascinating trivia. It's grounded in rigorous, ongoing academic research. Take, for instance, this 2013 dissertation out of the University of Wisconsin-Madison, which focused entirely on the ecological and evolutionary aspects of sphagnum biology. Scientists are actively studying fossil evidence showing that moss-like plants have been around for over 450 million years. That is way before trees and way before the dinosaurs. They were literally among the very first plants to conquer the land, and we are still out there, actively unlocking the deep biological secrets of how they interact with temperature, UV light, and our shifting climate. Which brings us to our final thought. We started out today looking at a tiny, simple plant without roots or veins. And we've discovered an organism capable of pausing time, treating our wounded, and locking away a third of the entire planet's soil carbon. It is an absolute biological marvel. But as we continue to harvest peatlands and alter global temperatures, we really have to ask ourselves this critical question. If moss has successfully preserved the Earth's delicate balance for 450 million years, how will we ensure that we preserve the moss? Thank you so much for joining me for this explainer. I really hope this completely changes the way you look at the ground beneath your feet.